Schrodinger visualized electrons as wave-like for his mathematical equations, and so his equations are called wave equations. And all of these equations that he did, we use a Greek letter psi, so you'd say psi is how it's pronounced. And the Greek letter psi, this is his symbol for all of these mathematical equations. And they are three-dimensional equations, and he used them mostly in spherical polar coordinates, which use r, theta, and phi. And so you mostly don't need to worry about what these equations look like, and you don't really need to worry very much about spherical polar coordinates, but I will probably refer to them every now and then. And so I just wanted to be super clear in my upfront that that's what we're talking about. Mostly we will be visualizing these just in the r dimension, which is the distance away from the origin. So what these wave equations tell us is that, or what we are trying to describe using these wave equations, is that electrons exist not as physical particles that are orbiting an atom the way that Niels Bohr thought about them, but instead that they exist sort of as more like electron clouds. They are standing waves, which may not help you at all to think about this as a standing wave. A standing wave is like when you pluck a guitar string and it sort of vibrates back and forth, and it exists as this wave that takes up the whole space between where you are connecting the string on one side and then where your finger is holding it down on the neck. But I think that thinking about them as electron clouds is maybe a little bit more relatable. If you think about this sort of cloudy substance of electronness that is around the atom, I don't know, I have an easier time kind of imagining that. So whatever works for you. And just like with any cloud, some areas are more dense. So they would be like thicker cloudiness, right? And that means that there is more electronness, more electron character in those areas. And there are consequently some places where the electron is less likely to be, and some areas where the electron can't be. And these are called nodes. And a node is actually a place where the mathematical function is equal to 0. And mostly we will be drawing these as representations, but this is still important to keep in mind. Okay, so rather than orbits like Niels Bohr called them, I think that the name orbital probably is the sort of wave at Niels Bohr's original idea of orbit without it actually being an orbit, because electrons don't orbit. They don't, have a continuous track. They exist, as I said, as this sort of nebulous, cloudy area where you have some electron character. So we still call them orbitals. So orbitals describe where the electrons are around an atom. And we have 3 numbers that describe the shape and size, and these are called quantum numbers. Of these orbitals. And we have one more quantum number that finishes describing each electron. So one way to think about these 4 quantum numbers is that these 4 quantum numbers describe the address. They describe each electron's address in the atom. And it turns out that each electron has to have its own address, at least by a slightly different number. And this is called the Pauli exclusion principle. Each electron in an atom must have at least one quantum number that's different from all the others. And we'll see how this plays out in a little bit more later. Although we mostly, anyway, we'll talk about this a little bit more later. So let's just talk about our 4 quantum numbers first. So our first quantum number is n, which is called the principal quantum number. And this is the same n, lowercase n, that we used in the Bohr model and in the Rydberg equation. So this defines what we call the shell of the electron. And it's the approximate energy, or rather it approximately defines, maybe I should just say it's related to the energy. So larger n means higher energy, mostly. And it also means further from the nucleus, mostly. All right. So all of the n values that we can have, they have to be positive whole numbers. So 1, 2, 3, 4, any number, that's as long as it's positive, and it can't be 0. So our second quantum number is lowercase l, which is called the angular momentum quantum number. And don't worry about why these are called what they are, principal, angular momentum, etc. So just like the principal quantum number was related to the energy, this defines the shape of the orbital. And it also defines the subshell. So under the shell, and we have a subshell, which is based on our angular momentum. The L values can be any number that's smaller than the n. So we can go 0, 1, 2, 3, up to n minus 1. So any number that's 1 smaller than the n can be fine. So these angular momentum numbers are limited by the n value. All right, our third quantum number is called, or its symbol is a little m sub L, and this is called the magnetic quantum number. And this defines the orientation of the orbital. And this will make more sense when we visualize the orbitals in a little bit. Just like with the angular momentum quantum number, the magnetic quantum number is also limited by the values of the angular momentum quantum number. So the allowed values for m sub L can be 0, they can be plus or minus 1, plus or minus 2, up to whatever plus or minus the L value is for that particular orbital. Okay, and our fourth quantum number is m sub S, and this is called the spin quantum number. And this only has 2 values. The spin quantum number can be either plus 1/2 or it can be minus 1/2. And we're going to talk more about the spin quantum number a little bit later on and why it has these two values. Well, I don't know if we'll talk about why, but we will talk about how we're going to use it. So the other thing to know about the angular momentum quantum numbers is that these have special letter designations that we use to talk about orbitals. So our letters for the L values, if you have an L is equal to 0, then we call that an s orbital. And these are lowercase. All of them. For L is equal to 1, that would be p. For L is equal to 2, that would be a d orbital. For L is equal to 3, that would be an f orbital. For L is equal to 4, that's a g orbital, and then after that they go in alphabetical order. So if you have more than that, you just keep going in alphabetical order. So this S, P, D, and F, these are those letters for historical reasons. When people were first studying atoms, they sort of named some spectroscopy lines based on these letters. But anyway, that's the only reason why they're called that. Each orbital is going to be named based on the n value and the L value. So we name orbitals by the n and L values. And so, for example, if we have n is equal to 4 and L is equal to 2, then we look over at the L values and we see that L is equal to 2 is a d orbital. So that means that this would be a 4d orbital. Okay? So if you have n is equal to 6 and L is equal to 0, then you're going to look over and see L is equal to 0. That's an s orbital, so this is going to be a 6s orbital. Okay? So each type of orbital has a number of orbitals that are based on the number of each orientation. So what this means is that when I'm talking about something like a 4D, this is a subshell. 6s is also a subshell. And so we can count the number of orbitals in each subshell. So let's see what that's going to look like. Remember, this is based on the m sub L values. So let's just start by looking at allowed combinations of quantum numbers. Okay, so if n is equal to 1, what kind of allowed L values can we have? Pause the video and go take a look at your quantum numbers and see if you can figure it out. All right, so you should have noticed that L can only be 0 for this. And so that means that the m sub L value can only be 0 also. And of course, m sub s can be either plus or minus 1/2. So if n is equal to 2, oh, hang on, let's talk about the orbitals too. So since we have n is equal to 1, L is equal to 0, m sub L is equal to 0, that means we have one s and it has one orientation. Remember the m sub L, this gives us the orientation. So there is only one orbital in the n is equal to 1 shell and the 1s subshell. these 4 numbers describe the orbital. Okay, let's see how this looks when we have more combinations. So we can see what it's going to look like when we have, more more things in the shell and the subshell. So let's look at n is equal to 2. For n is equal to 2, we have 2 values of L available. We have L is equal to 0 like we did before, and we have L is equal to 1. So that means that this is one subshell, and this is another subshell. Just like before, the n equals 2, L is equal to 0. So this would be 2s, or 2s, subshell, has m sub L still only equal to 0. And so this still only has one orientation. So the 2s subshell has one orientation, one orbital. So now let's look at what would this be? This would be the 2p subshell. So notice now that the m sub L values, I can have 0, and I can have +1, and I can have -1. So now I have 3 orientations. And that means 3 orbitals. Of course, I still have m sub s equals plus or minus 1/2 because those are the only allowed possibilities. So that means that in the 2p subshell, we have 3 orbitals. And typically the way that we refer to these are 2p sub x, 2p sub y, and 2p sub z, just to kind of make it easy to refer to them differently from each other. So let's look at the n is equal to 3 shell as well. In the n equals 3 shell, we have several subshells, right? We have the L is equal to 0 subshell, the L is equal to 1 subshell, and now the L is equal to 2 subshell. So this would be the 3s, 3p, and 3d subshells. So same as before, m sub L still is equal to just 0 for the s orbital, and it still only has one orbital, one orientation. So all s orbitals, there's just one orientation. For m sub L, it's the same story we just had. 0, +1, -1, 3 orbitals. Now for the 3D, we have m sub L is equal to 0, +1, -1, +2, and -2, because we can go up to the value of the L. So let's count. That's 1, 2, 3, 4, 5 orbitals, 5 orientations, and 5 orbitals. All right, so let's take a moment here and ask ourselves, can we recognize allowed combinations of orbitals? So are these combinations, sorry, I don't mean orbitals, I mean combinations of quantum numbers. So I'm going to write some quantum number combinations down, and I want you to pause the video and look at them and see whether or not these combinations are allowed based on our rules. So this is going to be n, L, m sub L, and m sub s. Okay? So the first combination is 3, 1, minus 2, plus 1/2. The second combination is 4, 4, 0, minus 1/2. Next we'll go 4, 1, minus 1, minus 1/2. And how about 2, 0, 1, plus 1/2. So pause the video and think about these for a minute. All right, hopefully you noticed that this m sub l value is larger than the L value, and that's not allowed. We can have m sub l values that go up to the size of the L, but not larger than it. So this is not allowed. We would need to change either this L value to be bigger or this m sub l value to be smaller. So if I wanted to propose a change, then maybe I would just make this value 2 instead, and then it would work. All right. Now in the second one, I hope you noticed that this L value can't be the same as the N value. So it is not allowed to have the N value not be larger than the L. So that is a change we could make. We could just change that N value to 5, and then this would be an allowed combination. All right, and the third one here, this is fine, right? We have L, which is smaller than N. We have M sub L, which is smaller than or equal to M sub L, or excuse me, L, and it can be negative, that's fine. And our M sub S values, they are all okay. There's nothing wrong with any of them. So in this last one, notice that we have the same problem here that we did up at the top. Our M sub L value is bigger than our L, which is not allowed. So we could make this number smaller, or excuse me, larger, and then we'd be fine. Or we could make the M sub L value smaller. So hopefully you can now recognize what are allowed combinations of quantum numbers. So as we are going forward, we are going to be looking at quantum numbers, we're going to be identifying them, and what I want you to make sure that you can do is you can recognize which ones are allowed, and you should remember the L values and their letters. So I'm going to pause the video here, and in the next video we're going to talk about orbital shapes.